All right, so here we have our example of, or we have our kind of guiding principle here looking at our graph. The first thing we're always going to do when we're trying to deal with one of these graphs is to factor and simplify, absolutely. Okay, if we can. I have a feeling with this one we're not going to be able to simplify, but it's a good idea to go ahead and factor it out if we can. So my big X here, and I'm off the page. So my big X is on the top I would have a 10, and on the bottom I would have a -5. So I'm looking for two numbers that multiply to 10 and add or subtract to -5, and it doesn't look like there are any. So in this particular case, I'm not going to be able to simplify this at all, so I'm just going to go with the function that I have. Right? So vertical asymptote. So looking at the vertical asymptote here, well, the vertical asymptote is when our simplified function has a denominator equal to 0. So, well, this is our simplified function. So let's go ahead and set x minus 2 equal to 0. If we add 2 to both sides, then we're going to get x equals 2. Well, looking at our graph, we can see that that pretty much makes sense. We'd kind of predicted before that there was going to be a vertical asymptote right there at x equals 2. So it kind of is affirming our beliefs there. Now, horizontal asymptotes. Okay. The horizontal asymptotes, what we're basically looking for, okay, is a relationship where when x gets really big, or as x approaches infinity, or x approaches negative infinity, well, what's going to happen? Well, looking at it, if I look at my big powers, I have an x squared over an x. Well, that x squared is going to get big way faster than the x, right? And as if we put like 10,000 in there, that's going to be a much, much bigger number than this. So we learned before, and one of our rules simply is that if the degree of our numerator is bigger than the degree of the denominator, there is no horizontal asymptote. Okay? And the idea is that as x gets really big, the top number is going to get really big. So y will simply approach infinity. Yes? All slant asymptotes, I think by definition, I mean, one of the things is that that's a good point. Okay? By definition, all slant asymptotes have a bigger degree in the numerator, right? By definition. So if it has a slant asymptote, unless there's a weird example that I'm not thinking of, no, it won't have a horizontal asymptote. Okay? So slant asymptote. Well, remember, slant asymptote is when the degree of the denominator, or numerator, sorry, is 1 bigger than the degree of the denominator.
You can use synthetic division.
And this one we can use synthetic division. So I can see here that 2 is definitely one bigger than 1. So this does have a slant asymptote. Now you divide to find that slant asymptote. So in this case, we can go ahead and we can use synthetic division because this is a linear divisor with a lead coefficient of 1. So if I want to know what to divide by, I need to find the 0. So I set x equal to 2. X minus 2 as a factor will give an x value of 2. Okay, we do some synthetic division. Well, I'm going to do 2 is going to go into 2, -5, 5. I keep doing that. Give myself space. There we go. Okay, so I bring down the 2. 2 times 2 is 4. Leaves me with a -1. 2 times -1. Well, I'm going to complete it, but it doesn't matter. I get -2 and 3. Well, I know now then that my slant asymptote, and I'm going to go ahead and just kind of extend it down here so I have more space. The slant asymptote is y equals 2x minus 1. Okay?
So you just disregard the remainder?
The remainder doesn't matter. Okay? So we divided by x minus 2, and we were left with coefficients of 2 and negative 1, or 2x minus 1. That's our slant asymptote. Okay? Now, to find the x-intercept, which from our graph we can be pretty confident we don't have an x-intercept, but we set the output equal to, okay, at the x-axis, our output is always 0. So we set it equal to 0. Now, a trick for this is we don't have to remember the whole trick about the numerator if we just set up a proportion. Over x minus 2, well, 0 we can write as 0 over 1. So 0 times x minus 2 is just 0. And 1 times our numerator, okay, cross products of proportions are equal, so we get 2x squared minus 5x plus 5. Now, one thing that you're going to find is in this particular example, if you plug this into the quadratic formula, you get imaginary numbers. I'm not going to go through the process. You can check it on your own. Plug it into the quadratic formula. You end up with a negative under the square root. And we can see from our graph here that we don't expect to find any imaginary numbers for this, or any x-intercepts. And it does line up as being correct. Now, to find the y-intercept, we set what's true about every point on the y-axis? X equals 0. So for here, we're going to set x equal to 0. Anytime, it doesn't matter what function you're working with. If you want to find the x-intercept, you set y equal to 0. If you want to find the y-intercept, you set x equal to 0. Then you solve. So we want to know what f of 0 is. Well, we go ahead and we plug everything in here. Well, I'm going to get 2 times 0 squared minus 5 times 0 plus 5 all over 0 minus 2. Well, that's going to go away, that's going to go away, and we're just left with 5 over negative 2. So our y-intercept is going to be at 0, negative 5 over 2. And negative 5 over 2 is equal to negative, 2 and 1/2? So when we're graphing, we can use that. Yes?
So basically, like on our benchmark, this is what we're going to fill in all of those?
We're going to probably just be asked to graph and then compare it to the graph. So you'll need all this information. Okay? Yes, Rena?
So for x-intercept, you just put x1 if you have an imaginary.
Yep, this one has no x-intercept. Okay? Now, going through and graphing it, again, if you have different colored pens and stuff like that, it can be helpful, but use a dashed line for any asymptotes. So for the first asymptote, we go and we see we have a vertical asymptote at 2. So let's go ahead and draw that. Vertical asymptote at 2. Then I look and I don't have a horizontal asymptote, so I'm going to go to the slant asymptote. I'll go ahead and do that one in blue. Slant asymptote, it looks like we had that. It was at y is equal to 2x minus 1. Now you graph this like you would any other line. We have a y-intercept at negative 1, so I go down to there, get 1 point, and then we have a slope of 2. So I go up 1, 2 over 1, up 1, 2 over 1. Do a couple points just to make sure that we have a nice straight line. And if we had a y-intercept here at 0, negative 5 over 2. So x is 0, and then we're right at about 2.5. Now, here's where you start guessing. Okay? We need some additional points. We have all of our critical points. Now we just need a few to fill in the blanks. Okay? Now you're going to want to base those points off of, well, remember the vertical asymptote is, you can never cross it, right? So base them off your vertical asymptotes. We need to know what we do when we're to the left of the vertical asymptote and to the right of the vertical asymptote. So let's pick some points. Okay. Well, it's at 2, so let's maybe try f of 1. Start with f of 1. Okay. If someone can calculate that for me, please. Okay. Then we could do f of, let's do maybe f of negative 2. We'll go over to the right here a bit. F of negative 2. Sounds pretty good. And then let's go to the right. So these are to the left of the vertical asymptote. Let's do a couple to the right of the vertical asymptote. So let's do 1 to the right. So f of 3. And then let's maybe do like 3 to the right. So f of 6. Okay. And if I can get some people just to plug those in their calculators or just get those calculated out real quick. Okay. Has anyone gotten f of 1 yet? It's negative 2? Okay. What about negative 2? Did we get that one? Okay. Well, I'm going to cheat and look at my calculator, but just plug it in the way you normally would. Replace every x with that value. It's negative 23 over 4, or since we're going to be graphing it, mixed numbers work out pretty well, so we would do negative 5 and 3/4. Hey, anyone get f of 3? Okay, we got 8. And f of 6, that looks like it's 47 over 4. Okay, and that would work out to 11 and 3/4, which is actually going to be a little off the graph, so we'll kind of play this by ear a little bit. All right, so now you just plot points. Here we have 1, negative 2. So when x is 1, we're at negative 2, right about there. Okay, and when f of negative 2, so we're over here at negative 2, we're at 5 and 3/4, negative 5 and 3/4. So 1, 2, 3, 4, 5 and 3/4, right about there. So you can tell that the curve is probably going to look something like this. Okay, it's going to curve around and then it's going to start approaching our vertical asymptote but never quite get there. Okay, everyone see that? All right, now we're going to go ahead and go to the right of the vertical asymptote. Well, when we're at 3, we're up at 1, 2, 3, 4, 5, 6, 7, 8. So we're right about here. Then when we are at 6, so at 4, 5, 6, we're actually up at 11 and 3/4. So we're going to be up here about. So we can tell, you should be able to tell, our graph's going to do something to the effect of this. And it doesn't have to be perfectly accurate. We're just trying to get it to where we have all of our critical points correct, and then we have enough points to make a fairly accurate sketch. All right?
Will this part be on Thursday or Friday?
Most likely Thursday. I'll take a look at the test tonight.